this, in a nutshell, is the process of defining your design onto the surface of a substrate. And the way it works is we spin what's called a photoresist layer onto the substrate. This is done at high RPM, so we get a nice uniform coating. And this contains a photosensitive compound that's suspended in a solvent. So once we've done this spinning step, we then bake the wafer, and that evaporates the solvent, leaving behind our photosensitive compound. And this will usually happen in a yellow room environment, and it's yellow because it filters out the wavelengths of light that actually interact with the photosensitive material. If any of you are keen photographers, this is, almost exactly the same concept of how you develop an old school photograph. So once we've got our photosensitive layer on our wafer, we then put it into a lithography tool and we expose it to light of a particular wavelength, but it's a selective exposure. So we have a mask layer that blocks particular regions of the wafer and exposes others. And this causes a chemical reaction in your photosensitive layer that when we then subsequently put it into a developer, the exposed regions, if it's a positive tone resist, are then removed by the developer, leaving the substrate exposed. Once we've done this, we can then go on to another step that could be an etch, it could be an ion implantation, or it could be a number of other things. And there are a number of different types of lithography. The three most common are listed here. There are more. The most basic is what's called contact lithography, and as the name suggests, in this case, we simply contact the mask layer on top of the substrate. And this is a very accessible tool that almost every clean room around the world will have access to. So it's very affordable, but it does have a limit in the resolution, because you'll get some diffraction of the light from the bottom surface of the mask. But a far more complex tool is a projection lithography system, and now in this case we move the mask away from the surface of the wafer, and we have a big lens in the middle. And in the little diagram there, it's shown as a single lens, but in reality it will be a very complex sequence of lenses, and that lens focuses the light that's coming through the mask onto the surface of the wafer, and usually it will shrink the image. In the case of the tool that we have, it's by 4 times. So what this means is that it reduces the requirements on the dimensions in your mask, because the dimensions you achieve on the substrate are 4 times smaller than on the mask. This is really a mass production tool. The latest tools are capable of doing several hundred wafers per hour, and it can have a very good resolution, down to sort of 25 nanometers for the very expensive state-of-the-art tools that tend to not be used for silicon photonics, because that's really overkill. But there are more affordable sort of legacy tools that have a higher resolution limit, but I'll come on to that on the next slide. Another very common lithography tool is an electron beam system. This is different from the other two in that it's a direct write tool. So we fire a beam of electrons at a resist layer that in this case is sensitive to electrons. But it does mean that it's a very slow process. We have to effectively draw everything that we want on the wafer. So if I compare that to projection lithography, it literally could take, say, 2 days to go through writing a waveguide layer on an 8-inch wafer using E-beam. But the best thing about it is that we can achieve a very high resolution, because clearly the wavelength of an electron is much smaller than that of light. So this gives you the very best in terms of resolution and capabilities. So a little bit of detail about projection lithography, there are a few different systems that are commonly used in silicon photonics, and I've listed the three most common here. And the 248 and 193 refers to the wavelength of light that we use. I've listed the sort of typical resolution and overlay alignment parameters on the slide, so I won't go through them. I would say that the more legacy tools are useful for prototyping, because you can access them in both 8-inch and 12-inch. The later tools that are higher specification generally are only available in 12-inch, so that, you know, it becomes far more expensive to access these, but clearly you can achieve better performance from them. So this is just a video of our lithography system. Here we're loading a cassette of wafers. It's all automated and handled by robotic arms. So what we're doing here is loading a wafer. We're now spinning it. Here you'll notice it's spinning at very high RPM. We're coating it with a photoresist layer. We're now going to move it to a hot plate to bake it. And then it gets passed into the scanner. What we didn't show is that actually there's a preliminary step of spinning it with an anti-reflective coating. So there are actually two layers that we spin on. This is the process of patterning the die on the wafer. Here it's sped up. And once we've done that, the wafer gets passed back into our track system, and the development process happens. So this is the development being automated in this way. Everything could be very controlled, and here we have our nice output wafer.